All right, so let's continue. This is the second part, and to get started on the second part, I want to focus on the example that we looked at. All right, so we had this example, spring mass damper, okay, and then there was some forcing function, and the position is x, and it's k, b, and m. Okay, and what we showed is that we were able to, after taking the Laplace transform of the differential equation, we were able to show that x of s is equal to s plus 4 over either s plus 1, s plus 2, s plus 3, or also s plus 4 times s cubed plus 6s squared plus 11s plus 6. Okay, so one thing that's important here is that you realize that the Laplace transform is it's always going to come out as a polynomial of s, okay, in terms of s, over another polynomial. So right now we have a numerator and a denominator as that are polynomials of s. Okay, and you know that polynomials have roots. Okay, so for example, this polynomial, the root is minus 4, right? Because root meaning when I ask, let's say, when I say the denominator of s is equal to 0, or the numerator of s, if I set that polynomial equal to 0 and find out what s's, they will give me the roots, right? Roots are the values of s that will give me my denominator or my numerator, whatever polynomial will make it 0, right? Okay, so roots of these polynomials are going to be very crucial throughout this whole class. Okay, so I just want to, really understand that you can find roots for the numerator and the denominator. Let's look at it on MATLAB actually. So here, it's not always as easy to see what the roots of that polynomial is. Okay, but if you can factor it out, it's obvious, right? If s was minus 1, I'd get 0. If s was minus 2, I'd get 0 for the polynomial. And if s was minus 3, I'd get 0. So I've got 3 roots, which makes sense because it's a cube polynomial. Okay, so or I should say the polynomial is the highest order of 3, so then you're going to have definitely 3 roots. All right, so let's flip over to MATLAB real quick and let's just double check this, and I'll show you a few tricks. So here you see that I have 1s cubed plus 6s squared plus 11s plus 6. All right, so let's take a look at that. Now, how do you define polynomials in MATLAB? Well, you define them, there you go, as a vector of the coefficients in front of the polynomial. So 1, 6, 11, and forgot it already, and 6. 1, 6, 11. All right, 1, 6, 11, and 6. Okay, so there's that's just a vector, all right, but I can do things like, for example, I can do a function called look for, and it's going to look for anything that has roots in the help. All right. So if I flipped, and probably most of you guys should have seen roots. For some reason, MATLAB is being extremely slow on me. So look for is a nice little tool. There it is. Okay. So I'm just going to hit Control C to get out of it. There you go. All right, Control C will get you out of it. It was still searching, and I didn't care for it. So here is, oh, this is interesting. I've never actually used poly, but roots I've used. So if I go roots of poly, oops, I missed. Okay. then what you'll see is that I took that s cubed plus 6x squared plus 11s plus 6, and it gave me minus 3 minus 2 minus 1, which we already knew, but that's just, I was just double checking to make sure. Alright, now let's see if this poly works. If I go minus 3, minus 1, minus 2, minus 3, let's see what it does. You know what, the problem is this is an important actually mistake I made. I didn't realize there was a function called poly, and what happens is what I just did was overwrote the poly function in some sense. Now when I restart MATLAB, this poly function will work again. All right, but right now when I call poly, it's not pointing to this function, it's pointing to my vector that I made. Alright, so a lot of times it's useful to use capital letters in your variables so you don't make those kind of mistakes. So I'm not going to bother to restart MATLAB. I just wanted to show you that. I was hoping it would show you an example. But my guess is if you did this, it would give you this polynomial right here. It would spit out this polynomial. Okay, try it. Alright, so now that we understand roots of our numerator or denominator, from now, for at least this next few lectures, or this Laplace lecture, what we really care about are the roots of the denominator. Okay, at this point, the denominator, the roots of the denominator are crucial, while the roots of the numerator are important, but not for this lecture. Okay, so at this point, I don't really care what the roots of the numerator are. We'll talk about the numerator roots later. All right. So now that we understand that we care about these roots of the denominator, now we can ask ourselves a couple questions. All right. Are the roots of the denominator, 1, distinct and real? Are they distinct and complex? Or finally, are they repeated, either real or complex? Okay, so we're going to spend time on each one of these sections. So doing partial fraction expansion for each one of these there's a few tricks for each one separately. All right, so I'm going to start off this lecture and I'm going to focus on the fact that the roots are real and distinct. Okay, so for example, the example we've been working on, the roots were minus 1, minus 3, and minus 2. Okay, that was weird. But anyways, these fall into, they are distinct because they are not repeated. There's not a minus 3 and another minus 3. And they're real. Okay, those are real numbers. They're not, I should say, yeah, they don't have any imaginary portion of it. Okay, so let's stick with that, and then I'll make another video, 2 more videos for distinct and complex, and also for repeated roots. All right. Okay, so now that we know that they are distinct and real, all right, let me just say partial fraction expansion for real and distinct roots. Okay, that's the main topic we're going to talk about for the rest of this lecture. Okay, so it's simple. All right, let's say you have n roots. Okay, n roots that are real and distinct. Okay, then your x of s is going to be equal to a over s minus the root, and let's say these roots are, let's call it p1, p2, p3, dot dot dot, pn. Okay, then you can write your the partial fraction expansion as ps minus p1 plus b s minus p2 plus dot 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 all the way to whatever letter over, so, and I could have made some, these are all constants, over s minus pn. All right, this is true. Everything's going to look different when I go to complex or repeated. It's going to look somewhat similar, but some other tricks. Okay, so let's go ahead and use the example as a starting point to understand what's going on here. All right, so back to our example. We had x of s is equal to s plus 4 all over s cubed plus 6s plus 11s squared, 11s plus 6. That is going to be equal to a over s plus 1 plus b over s plus 2 plus c over s plus 3. Okay, and our job now is to find out what a, b, and c are. Those are just coefficients. All right, and once we find out, remember this is s minus the first root, which was minus 1, so s plus 1 and so on. Okay, we have 3 roots, right? Write that again. Minus 1, minus 2, minus 3. Okay, so guess what? Once we find out a, b, and c, then I can easily do the Laplace inverse of x of s, which is equal to x of t, which is what we're trying to find, which is equal to the Laplace inverse of this, and if you remember, this is just an e to the minus minus t, and minus 2t and minus 3t. So it'll be a e to the minus t plus b e to the minus 2t plus c e to the minus 3t. And that's just the inverse Laplace, right? That's just the inverse Laplace of these guys. Okay, that's it. So actually, as you can see, real and distinct roots, finding once you know that your Laplace transform has real distinct roots in the denominator, then actually it's really easy to come out with what form the output will be. Okay, here's the thing: we still haven't found a, b, and c. All right, so let's talk about. There's a few different ways to do it, to find a and b and c. And then once you find a, b, and c, we're done. Okay, so actually real distinct roots are pretty simple, in my opinion. All right, gets a little trickier when we go to complex, and we'll look at that. All right, so let's see. So how do we find a, b, and c? All right, there's a few different ways. All right, I'm going to go ahead and I'm going to say method, that's method 1, okay? And I'm going to call that equating coefficients. All right? So let's look at what x of s was equal to. X of s for the example, so we're back to the example, was s plus 4 all over, let's see, s plus 4 all over s plus 1. Oh, you know what? I think I messed up. S plus 3. No, let me double check. No, I'm okay. S plus, so that was true, and then that was equal to a over s plus 1 plus b over s plus 2 plus c over s plus 3. Now again, this hopefully is some type of review, because hopefully you've seen partial fraction expansion in some other class. All right. So now what I'm going to do is I'm going to multiply this denominator by both sides. Okay? And here's what it's going to look like. If I multiply through, I get s plus 4 is equal to, now the s plus 1 and the s plus 1 cancel, and that leaves me with this s plus 1 times s plus 3, and I'm going to do the FOIL out as I multiply. So I'm going to get s squared plus 5s plus 6 times a, and then I'm going to get plus, and then when I multiply it times this, the s plus 2 cancels, so I'll get s squared plus 4s plus 3 times b, and then this one disappears when I multiply it by here. They cancel out, and I get plus s squared plus 2s, no, sorry, plus 3s plus 2 times c. Okay? And now I'm going to collect the s squareds, the s's, and the constants together. Okay? So here's what I get. I get, well, for the s squareds, I get a plus b plus c times s squared, plus, let's see, for the s, I get, that's a 5s, right? So I get 5a, 4b, and 3. So 5a plus 4b plus 3c times s. And then the constants are going to be 6, 3, and 2. So plus 6a plus 3b plus, plus 2c, and then that's it. Okay? So now we're just about finished. If you compare both sides, okay, and this is why we're equating coefficients. So think about this. There's a 0s squared plus a 1s plus 4. All right. So what does that mean? A plus b plus c have to be equal to? Well, if you compare the coefficients, you see that it has to be 0. Okay. What about 5a? So 5a plus 4b plus 3c must be equal to 1. Okay. And of course, 6a plus 3b plus 2c equals 4. 3 equations, 3 unknowns. Okay, I can solve for it. All right, I'm not going to go through it because I want to show you another method that's actually is quicker. Although this method, I've always liked this method. It just sort of made sense to me. But there are, I would say it's slower. Okay, so let's go ahead and let's look at method B. Okay, so flip it over. All right, hold on one sec. All right, so here's method 2. Okay, and that is finding the residues, and I guess I didn't define what a residue was. Residues directly. Okay, the residue, if I go back one page, these are the residues. Okay, the coefficients we're talking about. All right, so you might have heard of residues before in math, especially when you're talking about partial fraction expansion. All right, but basically, how can we find it directly, find A, B, and C directly without solving these 3 equations, 3 unknowns? And I'm going to show you how right now. Okay, but this works only if you have a real distinct root. Okay, or I should say a distinct root. Okay, so again, I'm going to rewrite. So I had x of s is equal to s plus 4 all over s plus 1 times s plus 2. I should have a stamp for this. S plus 3. And that is equal to a s plus 1 plus b s plus 2 plus c s plus 3. Okay? So, what I'm going to do, I'm going to do a little trick. I'm going to multiply by s plus 1. Okay? So I'm going to take s plus 1 and I'm going to multiply it by x of s. And then I'm going to do something important. I'm going to evaluate s at the root, at minus 1. All right? So I could say, let me write it in general terms. I'm going to multiply x of s times s minus p1, which is just that, or that, and I'm going to evaluate it at p1. Okay. Now, I could do not, and I'll do it with p2 and so on and so forth. So let me go back. I'm going to write down. I'm going to actually put the values in. Okay. Now, if I multiply by s plus 1, I think you'd agree that this side is going to be s plus 4 all over s plus 2 times s plus 3. Okay, and I'm going to evaluate it at s equals minus 1, so we'll get to that. Actually, I could just do it real quick. That is equal to, if I put in minus 1, I get 3, 1, and 2, so 3 over 2. All right. So if I write 3 over 2, so that is just this portion. Now I'm going to do it over here, and that's going to be equal to, well, if I multiply this whole side by s plus 1, I get a plus s plus 1 times b over s plus 2, and plus s plus 1 over s plus 3 times c. Now look at this trick. Now remember, we are evaluating at minus 1. So guess what happens to these two terms when I evaluate at minus 1? Well, minus 1 plus 1 is 0, so all these go away. And that's the beauty of it, and what you get left with is a and 3 halves, and we're done. Okay? So that was a. So let's find b. Same method. I'm going to multiply by s plus 2 times x of s. Evaluate it at minus 2. So multiply by, so that's s plus 4 all over s plus 1 times s plus 3. Evaluate at s equals minus 2. And I get 2 minus 1 and 1, so I get minus 2. All right. Let me double check, make sure I'm doing my math right. I got it here somewhere. All right. Where did it go? Well, anyways, we'll assume that I'm doing my math right. Okay. So that's equal to minus 2. And then I've got to do this side, but I don't. It's going to turn out to be exactly like this, but I get left with b. All right, you can test it, but if I multiply by s plus 2, it gets canceled here, gets multiplied by this one, and evaluate at minus 2, they go away. Okay, so here is your b. Here's your a, here's your b, and now let me go to the next page to do c. Okay, so now c, I'm going to multiply s plus 3 times x of s, evaluated at s equals minus 3, and that's going to be equal to s plus 4 and then s plus 1 times s plus 2. Evaluate that at minus 3, that's going to be equal to 1 minus 2 minus 1, so 1/2. Okay, and that's going to be equal to c. Okay, a, b, and c. Now I can write down the solution. X of t is equal to 3/2 e to the minus t minus 2 e to the minus 2t plus 1/2 e to the minus 3t. Done. Okay, so that's the method. Remember, this is for real and distinct roots. Let's stop here and move on to distinct and complex roots. All right.